it makes it much more interactive. I think it can be much more interesting this way.
Yeah, I've also actually deliberately left out this part of the code to look at it, so I can have some genuine questions that might come up with somebody who's actually also new to the code.
Okay.
I mean,
cool.
some things I guess are already known, right? Because I mean, for example, the block levels and all of these kind of things you see all over the place, but the storage layer is actually something that I haven't really looked at yet.
Yeah. Yeah. Okay. There's a lot to cover, so let's start. May it go well. Okay, I'm turning off my camera. So just to go over this roadmap, more or less, we're going to walk through. So I might need to introduce a storage layer, like you just said, basically, and then explain pruning. I guess it's going to be like a DFS, a depth first search. Like we're going to have to, if we encounter something you don't know enough about, or we need to explain, I guess we'll just go zoom in for a moment and then get back up. So I'm going to try not to go too much into things like reachability internally, covered in the previous workshop, but we will need to understand like more or less what's happening when we prune a block in terms of the topology around it. I think because that's my I never benchmarked. I'm actually leaving. Yeah, it's part of this task is to explain how it is to give the idea is to give the background for two tasks I can point at, so others can actually really deep dive and profile and figure out the solution from beginning to end. Yeah, I'm just going to try to give all the information that I have when I look at this problem. So explaining pruning, we might need to explain what multi-level relations are for both of the tasks, like it's related to both of them. Then why isn't it simple to prune? Essentially, it's because, I guess the gist of it is because we need to keep superblocks here and there without losing their reachability and DAG structure info. So you have to kind of delete a lot of information, but you still need to preserve what that information implies for the remaining blocks. So the most straightforward way to do that was handling the logic of deletion one by one and recovering. And that had a cost. That's what I'm going to try to cover with you. And then we can get to other possible ideas of optimizing that area. And the second main talk topic is the okay, thanks for another recording. Okay, and also explaining the header challenge. Like I'll just show you the header and the multi-level parents, and you'll see immediately the inefficiency. And we can discuss the compression scheme is really simple because the data just screams it. So it is pretty simple. I'll try to explain why it should be done. It's not a consensus change. We can keep the hashing algorithm the same. It's just a data representation change. And there are challenges when we speak about keeping relational info whatever. There's a challenge that needs to be, that I don't have a straightforward solution to, and whoever takes this needs to actually think and come up with something. Yeah, so it's not all like straightforward. Okay, does that make sense?
Yeah, I think it makes sense. I think starting with the multi-level relations is maybe the best idea, right?
As a background.
Yeah, so people get an understanding like how the DAG structures build with all the subtags, and because I don't think that people are aware of it.
Yeah. So should we look at added header, an example header for a second?
Yeah, I think that makes sense. And then maybe also explain how proof of work like rarely produces these blocks that have a higher proof of work than you're actually looking for, which form the super blocks of the different levels.
Yeah, okay. So that's the main prerequisite for both, I guess. So I'll just do a short, like I'll actually let's see how we use so there's a tool in the tool in the Rusty-Kaspa, a command line tool, which is called Kaspa CLI, which is the easiest way to access RPC info from the node. So yeah, we're planning on compiling that now. So let's anyway, kind of we do a connect. I'll just jump to a remote. And if I do something like RPC get,
it's really small, hard to see for me. I don't know if others can see it better. Yeah, now it's better.
it's all linking, so it's whatever. It doesn't really matter. I just want to also show this for a second. So we have some random block. Kind of, I don't need I am going to need the my local command line because I need to copy and it's a whole story. Let's just wait for this.
It's building. The coding in Rust almost building long.
Yeah, Windows is slower. Like that's why I moved to Linux.
I'm actually quite impressed already how fast the whole thing builds. Like when I was working for Iota and we had like, I don't know, 30 minutes build time or something. It's absolutely horrible.
Really? Wow. On a Rust system or what?
Yeah. Really, really long build times.
Fresh Air is suggesting to decentralize the recording effort. Next workshop, recording on-chain. I don't know what like on-chain is. I only know
10 pictures per second.
Wait, now I need, okay. Don't use this IP, it has nothing on it. Hmm. Okay, so right now you need this speaker. So it's easy to see the beginning of the header has this parents by level. It's like a vec of vecs. So with a simple you can obviously see that the first level, like we have this block has 7 direct parents. Let's see how many levels have the same identical 7 parents. So it goes 1, 2. I think it should be around 30. Then,
especially the higher levels will most probably not change very often, right?
The higher level, yeah, there's like an actually identical until we get here, and then eventually it starts narrowing down. Like approximately by half. Not exactly in this case, but there's like an area of noise, which is a unique per level, because that's where like the current difficulty is. We'll get to that. Then you can see additional like identical levels here and there. Just because these 3 blocks happen to both have like 2 more zeros than these. So there's like a slight level jump. And then you get to the very sparse area where it's actually blocks from a few minutes ago or a few hours ago or a few days ago. But also here you can see some sequences where the level didn't change, like probably a block with 70 zeros a month ago, and there were no blocks with 69, 68, 67 zeros. So this is what you're going to see, more or less. Kind of jumping into, I know you know what superblocks are, so I don't know if I need to start from like... Anyway, this is the head of structure, and it obviously reflects some inefficiency in data representation. Might be the case that like on gRPC, for instance, which is used for peer-to-peer communication, there's a compression algorithm. So I guess it might capture a lot of this, but I'd love to see numbers. Like this can, like, whether or not the compression algorithm can help understanding if we only need to optimize the local storage, or we should also change the RPC scheme just to optimize this part as well. Okay, so I guess we need a whiteboard for explaining block levels, I guess. So I'm going to try and draw from my phone. I have a...
That's actually a good idea. Maybe I should do that. Because my mouse broke, so I cannot zoom, but it works with the little buttons on the side. So.
Yeah. So I have the pen, the thing for the phone, so it usually works pretty well. You see that, right?
I'm actually following your mouse. So.
Okay. So maybe can you give your like baseline intro to what superblocks are?
Yeah, okay. So generally speaking, when you do proof of work, you're essentially searching for hashes that have a certain amount of trailing zeros, right? And usually you have some kind of difficulty, like, I don't know, you want to have like, I don't know, 5 or 6 or whatever the current difficulty is. And every now and then you don't find a block that has, let's say, 5 zeros, but that it has instead 6 zeros at the end, or 7 zeros or 8 zeros. And this essentially depends how lucky you are. And every now and then you find something that has like a really large amount of zeros at the end. And this is what you then call superblocks, and you kind of maintain references to these blocks, long-range references, depending on the level, to earlier blocks. So that means, like, I don't know, here you would see like level 1, I guess, or 0, depending on where you start to count and how you enumerate them.
Like 0, this would be 1. This might be 2.
Exactly. And instead of just having references to the direct parents, you also maintain references to these older blocks, which allow you to traverse the DAG structure more efficiently.
So I was drawing only a chain to simplify the first presentation. Then, so in a chain, you would only keep a reference to the previous chain block at that level. So point at 0 and then point at the previous block because it happens to have another 0, and then point for an average. It would be 4 blocks back, which would have 2 more zeros. 8 blocks back would have 3 more zeros, and so on. So eventually you would point at these exponential distance growing blocks, where you actually point at, like, even if we're speaking BTC, which does not implement this scheme, but you would point like at a block with 85 zeros, which was mined a year ago, and represents like a huge amount of proof of work, in a sense, all compressed in that, because it's real. You can only find such a block even with such hash rate only once a few months. So it cannot be forged. No one can mine that block without that effort. So it represents so much proof of work succinctly, in a sense.
Yeah, you can also maybe as a short add-on, it's not supported by Casper right now yet, but you can build something which is called NIPO powers, non-interactive proofs of proof of work, where you can essentially create a succinct representation of these chains of superblocks, which allows light clients to validate the chain without downloading all the blocks and all the headers, which is quite nice if you want to at some point build, for example, chain interoperability into other chains, then they can just verify these succinct proofs, which are usually just like around a few kilobytes or something.
Yeah,
but I'm not sure. I guess we will have to see how, if that would be something that's possible in Casper, because if you prune, you kind of lose these superblock structure, right? But I'm not sure if you keep the superblocks above a certain level forever, if you prune them as well, if they go below a certain pruning threshold.
We keep the at most 2,000 blocks per level. That's actually, it's not us, it's essentially the idea of the original MLS. So essentially what happens over time, and as hash rate increases also, is that the top level with 2,000 blocks is increasing slowly. But you're obviously never going to reach a point where you have a block with 255 zeros, where you have more than 2,000 blocks with 255 zeros, because then we broke.
And then you broke proof of work.
You got to too much computational power that this universe cannot handle. So what happens is that the top level with 2,000 blocks increases. And when we compare, in a sense, if you compare two proof of work proofs of two nodes, and in the case where they don't have any shared ancestor, so if they have a shared ancestor, we can just like kind of measure the level where they have a shared ancestor and measure proof of work above it. But if they don't, the comparison would be what maximum level does these two proofs have sufficiently, like 2,000 blocks. So naturally, the network or the DAG representing over time more hash rate would have a higher level, having that criteria.
Yeah.
So that captures that, and essentially, you can say that the Caspa amount of headers you need to keep grows logarithmically over time, but it's actually bounded by a known constant of known physics limits. So it can be considered near constant or actually constant. Okay, like in a sense, like we mine now in an hour more than the amount of headers we need to keep for the entire history of proof of work of Caspa. So it doesn't matter, even if we go 100 BPS, the amount of succinct headers we need is still small. So, okay, so let's try and generalize like the chain to a DAG. So if we have a DAG, I should try and use colors maybe to, I'm not going to go into that.
Why can you change colors? Oh, no. Okay.
So when we looked at the chain, essentially like block number, the block I numbered 1 or 2 are, if you look at the subset of blocks belonging to level 2, so the references, the block we're referencing would be the tip of that chain, right? So the induced sub chain for that level would have the block on the left, this one. I'm not sure you can see my. No, you can't see my marking. Okay.
No, I'm also pointing at it, so they see my name.
Right. Yeah. So that block is going to be the tip of the subchain for level 2. So the same idea applies to DAGs in a more general structure. So say this block is these two are level 2, and we have a new block and it's pointing at these. And we have all these references. So meaning, what I'm saying is all these are belong to level 0 or 1. So the block at level 2, this headers can point at these blocks, and the topological or the set theory semantic is pretty simple. It's what block should I reference at level 2? So when I point at the two top, my direct parents, I induce a DAG, which is denoted by past me. Okay, past B. If this is block B, so the DAG we're looking at is the past of B, everything reachable from B. And if we look at past B and we reduce it to all blocks at level 2 only, so the tips are going to be those marked in gray, and those are the blocks who should appear at parents by level at entry 2. And when I say that we take the induced sub DAG at level 2, I mean that at that sub DAG you'll have a link and a reference between block. So it's kind of, you're only looking at blocks at level 2, so you're kind of dropping all the rest, but you're not losing their information.
Essentially having this kind of reference, right?
Yeah, and if there was like a block block 2 here, so both of them are going to point at it, even though they had no. Yeah, so they're obviously going to have references at level 2, but we could have induced those references also by only looking at the original DAG. Because essentially it's saying the previous block at level 2, which I had a path of edges going through non-level 2 blocks. So all the information is folded also within the original DAG, essentially.
Yeah, you could download all the intermediary blocks here in between and then reach those 2 blocks indirectly, but it would be quite expensive to follow all these references and like load them from this.
Right.
Find those
Which is
superblocks.
why, in a way, annoyingly, we need to keep in the header all the references explicitly, so we don't have to keep the original DAG throughout in order to understand this relation. So that's like the gist of superblocks and level sub DAGs and etc. So what happens, and why do we see like 30 levels with the same main? Why? Because the challenge, like the MLS paper speaks about a constant difficulty world. So it's assuming like constant difficulty. And then it's easy to just say, okay, normally you have no zeros, all blocks have no zeros or 1 0, and every 2 blocks you have another 0, so it's easier. But in a world where the DAG has changing difficulty due to DAA, this doesn't hold anymore. But you still, in a sense, you still value the block with 60 zeros in the same way. Like the noise at the lower levels is not the interesting part. Yeah, you're actually looking after the higher levels. And blocks with 60 or 70 zeros are the interesting ones. No matter exactly the difficulty, if the difficulty is around 30 zeros or 29 or whatever. So there's a zone where you no longer really care.
So essentially, the levels are static in relation to how many zeros you have at the end. It doesn't matter what the current difficulty is.
Right. But in order to make, so this was an annoying inefficiency. So we did like, we knew mainnet had one pause due to the bug 2 weeks after we launched it. So which was related to a much bigger inefficiency related to this area, I think. Also, there were a few other stuff. So we used that first hard fork, the 2 days down to, so we introduced a constant to consensus, which is saying, okay, we're assuming we're never going to get lower than a gigahash per second and main it. I think means at least 30 zeros. So we're kind of ignoring the first 30 zeros. We're assuming each block has at least 30 zeros, and we're only looking at the zeros after that for determining the level. So that makes it a little more efficient. So essentially we have only like 235 possible levels instead of 255 now, because we're kind of ignoring the beginning. So that makes it a little more efficient. So if you see like we have 30 levels identical, it means, or if we have 20 identical levels, it means that all blocks now have actually 50 zeros, more or less.
That's why they don't change.
Yeah, but even if we ignore the first 30 zeros, the next 20 zeros are still, all blocks have them. So all blocks are kind of on zero first, and 0 and 1, etc., going on until 20. And only then you start seeing the more sparse. So yeah, Coder is sharing all kinds of links. And the Coder was the one who did the most recent major optimization prior to Crescendo that was deeply related to this area. So he's an expert on this now.
It's a bit sad that people cannot see the link in the stream, right? But maybe we can just put it in the comments then later or something. I don't know.
Right, yeah, we can on YouTube we can add it at the description.
I'm just gonna copy the links and whatever.
So for me, if only we, yeah, so the fact that the header happens to have like these 20 identical levels, it doesn't affect almost any algorithm. Whatever it does is not critical. The only relevant area left is the actual data itself stored, and that's kind of an inefficiency because we also, besides the header, we also store actually relation. There's a relation store per level. There's actually like all this information. Essentially, there are 20 instances of the same data on the database. So we're not talking about huge amounts. It's probably like the overhead is probably a giga or two, but still a nice optimization to have. It was never critical enough, which is why it's a good task for people joining now. It's not like on the critical path of performance, but it's obviously going to speed things up. Like I'm assuming it might even have like a 2x factor. Or, I don't know.
Yeah, I guess it's also the amount of entries that need to be deleted later in pruning, which actually slows things down, right? It's not necessarily the amount of data, but just the amount of entries.
Yeah. Okay, so let's go back to the code and to the pruning logic. Any comments? Questions before we go on?
No, I think, I mean, for me, everything is clear. I haven't seen anything in the chat either, so I guess people understood it.
Okay, good. So my I changed some due to someone's advice. This word I changed to full. And I'm also going to zoom in where I can, but sometimes we need to see like the full picture.
Maybe
so in general,
make it bigger here. Not really. It's a bit hard to see the text for me. But this size is okay, I guess.
No, I can't. Wait. Okay. I'll zoom in as when I go into like specific lines. I'll do.
Okay.
Okay. So if we're looking at the left, there's general structure of a pipeline processor. Pipeline processing where we process headers, bodies, virtual state, and eventually the pruning processor is not so much part of the pipeline, but it is like it's receiving like notifications from virtual or the sync block, SINK, making progress. So it gets to the point where there's a new pruning point, which is deep enough so we can delete anything below it. So that triggers a prune process, which is in parallel to, kind of happens in parallel to the normal live activity.
How long do you maintain data? Is it like 24 hours or something, or longer?
So the data you maintain, the node would have between 30 hours to 42 hours by default now. Like the pruning period, like the jump of the advancement, the pruning advancement is done like every 12 hours. So right after pruning, you would have 30 hours of data, and then right before the next pruning, you would have almost 42 hours of data. Yeah, so when we analyze like worst case storage sizes, we take the 42 hours as a and previously on 1BPS it was more like 51 for the depth and another 24, so it was more like 75 hours. And the feature to keep to act, there's a configuration for the node where you can actually keep like any number of days you want. So you can actually do you can set it to 30 days if you want, if that's your retention period for whatever RPC you need. And then the node is going to prune the every day. It's still every 12 hours. It's going to prune 12 hours from 30 days ago. It's going to do the same thing, but yeah. So one of the challenges. So I'll show you the storage. So consensus storage looks like this. Okay, this is not so interesting. Let's focus on this. So there's the three major categories, I would say. Stores that have a lock, and stores that are append only. So stores that have a lock, meaning they'll store, or stores where the data can mutate over time. The most significant one is probably the reachability store and the relation stores. Both of these.
And those are also the ones that are being pruned, right?
Yeah, they like represent, in a sense, the way we maintain DAG topology. So they're the sensitive part. Yeah. So I just want to explain, like, on the other hand, you have a lot of significant stores which are append only, because you store the header once for a new hash. You just store its header. The header doesn't mutate anymore. We also have like ghost DAG related information, which is required for computing ghost DAG for following blocks. But the data itself for this block, from his POV, from his point of view, is static and never mutates. So that's also an append only store. Block transactions. Those are the most important ones for our. And then there are UTXO related stores, which are also append only here, because they also don't change. Like, you save the UTXO diff of a block from its selected parent, so that's like a static bunch of data. You save that only for chain blocks or previously chain, or any block which was a chain block at some point has this information. So this is append only semantically, which allowed us to optimize and avoid locking during normal processing. But then we got to pruning, and at pruning, you do write to this store, in a sense. You might, so the header processor might be looking at a parent of a block and might be assuming it exists. And then pruning might delete it. So it isn't append only in a sense. It is append only in one sense of the data itself doesn't mutate, but there is a possibility of the whole entry to be deleted. So how do you manage that? So the design we came up with, and I don't know if I'm convinced it's the best one, but it's kind of taking a few trade-offs also of complexity into mind. So there's a global pruning lock, which is normal processing. All normal block processing is a reader. It's a read-write lock, and all normal processing is a reader to that lock. So you can have a lot of entities acquiring it at once, and the pruning is the only writer. So, and that way we can manage. So it kind of guards all these append-only stores conceptually. It also guards like cross-store atomicity in a sense, because when the pruning acquires it, it kind of captures it and does a pruning operation, which logically is one operation, and when it releases it, all the readers know they can assume normal, whatever they assume normally about the state. If they looked at the status and the block status was some indicating that it should have transactions, so they can go and access the block transactions store without worrying that it might be deleted in between, because they are acquiring the read-only, the read side of the global lock. So this global lock is it's passed all around. It's actually like a custom implementation.
Nice. So I think I've seen it. So you let the other one starve, right? So if you're reading, the writers won't interrupt the readers.
Yeah, actually, went deep into semaphores and took some ideas from existing libraries, but also had to tweak them a bit. So the usefulness of this one is that it actually allows reentrancy. If a reader it's easy to use for the readers, they can actually acquire it as much, many times. There's no problem, and it also can be weighted on. It can be weighted also. It can have also a blocking weight and an asynchronous weight. So
how do you make sure that the pruning thing doesn't starve, like that it doesn't get locked out forever because there's always readers?
So live processing is doesn't take full resources, and we make sure to only lock for smaller segments. We don't lock the whole. We don't lock from the beginning of the block processing to the end. We avoid locking when not possible. If you look at it, there's a session manager, and it has a blocking set, a guarded session and an unguarded session. So for many, I don't know if we should go into that too deeply, but essentially there's within consensus processing pipeline, we're talking about normal threads. So they all do blocking reads. If we look at the header processor.
I think there's a begin task and end task.
Right. That's more for managing the dependencies between header processing, that we process headers only after we processed all their parents. So that's
okay, that's just for the causal order. So that's not related to the locking. Okay.
No, the locking itself happens when you actually get the task, this line.
Okay.
You would also see this if virtual process. So virtual process. So this is a fine-grained point because it's a per header. We don't expect this to take too long. So it's a very it doesn't starve the prune thread. If you look at virtual, you'll see we do it more carefully, because virtual resolving is more of a batch operation. It's not necessarily happening on a specific block. It can actually compute a reorg. Might be a few blocks deep, or in the worst case more. So when we do the virtual processing, we only lock minimally. I think we do this here. We drop it. We do it more carefully.
Okay.
So yeah, and in terms of like the prune not catching the write for too long, that's like explicitly managed. So he's the only place in the code where we acquire this lock
Right.
for writing is here. And we make sure to release it. For instance, it's released here. And then we acquire it. And then we do this. If lock acquire time is more than 5 milli, we do a yield.
Okay.
Yeah, which you would see it goes directly to this semaphore. It does, yeah. Slightly sensitive area, but this. I am showing you this because maybe Windows machines. I don't think this affects the efficiency of the pruning. Maybe the yield doesn't work as well at some scheduling, depending on the scheduler of the operating system, and maybe that's why. No, I don't think so.
Actually, Windows doesn't have such a has a really large how's it called? Not the English word, precision when it comes to these kind of delays and stuff. So it might be that maybe Windows blocks long or not as long or something. But other than that, I think it should work.
It says here that Windows is actually is faster. Like
more precise.
Even like
faster
in here, more precise, meaning even just doing the timeout for 10 macros was already enough for the readers to capture.
Okay.
I don't know.
That's unexpected.
Yeah, I don't know if I checked it too deeply, but probably the numbers I got from some machines, and that's what I wrote in the comments. And then there were no problems ongoing, so it just. Okay, so that's the overall picture of how the locking storage system works, more or less.
Okay.
So with all these prerequisites done, we can look into logic now. Is it just me or what? No, I think you can hear
me. You. So I assume that somebody would have already said something.
Yeah. It's just you. Sorry.
Yeah, but maybe we should write, otherwise he's not going to hear.
Yeah, no, Fresh Air is writing.
Okay.
Oh, yeah, I was talking to him. That's funny. Okay. So prune, essentially, what we do at the beginning is, like I described here. What is kept and why? So there are two major things we keep. The first one is the proof blocks. Like we actually generate the pruning proof, which pruning proof is a vector of headers. And it's the what we described earlier. It's the max 2,000 blocks per level. So at higher levels, it's not going to be 2,000. It gets smaller and smaller, but it means all the super blocks essentially we want to keep. And we keep the super blocks. We count the 2,000 from the pruning point and below. In a sense, we're trying to encapsulate all the proof of work information below the pruning point. Above the pruning point, we have the actual full bag, so we don't. Yeah, so that's how we
full data availability.
Yeah. So the proof. So all these proofs, the proof headers, as the reason we don't hesitate. Also, it's like within the pruning proof manager, we actually cache this proof in memory. So there's no like, yeah.
How big is that
No
right now?
reason not.
Do you have any estimate? Like how much memory does it
has
consume to have this thing cached? Shouldn't be too much, no?
It has around maybe, I think around either 15,000 or 30,000 unique headers. So I'm saying unique because a lot of the first, as you know, a lot of the first 20 levels, like the first 20 levels are probably identical mostly. So we use an arc here, if you can see. So
and do you deduplicate that somehow? Do you like have like a lookup table or something where you provide indexes to the different headers so you don't have to store them separately?
Yeah, that's a recent optimization, by the way. Cache. You can read the comments. The pruning proof can contain many duplicate headers across levels, so we use a local cache in order to make sure we hold a single arc per header.
Yeah, okay.
And we do the same. You might also be receiving the proof on RPC. So also, so the RPC itself sends the duplicates. It doesn't like it duplicates and sends you each copy. But when we get it and save it, we actually do the same strategy of realizing we have a duplicate and only keeping one. So the other thing we need to save besides the proof, the headers from the proof, is what we call the pruning point anticon data and trusted blocks. So that's data. So it's also the pruning proof manager, get pruning point anticon and trusted data. I want to explain this for a moment. So this represents all the information that if someone, another node needs to sync from you, it represents all the information it needs in order to process the blocks above the pruning point. So also blocks above the pruning point still need to access DAA information. They need to look at the DAA window, which is approximately composed of blocks from the last hour. And they need to be able to compute the difficulty. We want full validation for blocks above the pruning point.
You could also, in theory, have like a really long reorg, right? I mean, it's most probably never really going to happen in practice, or not very frequently at least, but in theory.
Right, but the pruning point is assumed to never
it's the point of no return.
Below. Yeah. Actually, the pruning point is the assumption is that finality point, which is currently 12 hour deep. That's like a no reorg point in the sense that actually the node would subjectively reject a reorg below that point. And if such a reorg happens, and some of the let's not go into that, but it's kind of the assumption that the work, not an assumption, it's enforced by the node decision to never reorg below the finality point. And the pruning point is combinatorically calculated to be deep enough so that any new block processed would not need information in its past.
Okay.
The actual combinatoric proof, we call it prunality proof.
Prunality.
Prunality. So, yeah, but when you look above the pruning point, you still need like the DA window. So it's kind of you kind of need the last hour before the pruning point, more or less in full.
Yeah.
And you also need some of those blocks for computing GoStag. You need some information from GoStag which is carried. So in order to verify GoStag correctly, you might need to go k chain blocks back in order to check the amount of blue blocks. So when you run GoStag for a block slightly above the pruning point, you might also go back a bit. So that's what we call trusted data. It's trusted in the sense that when you sync from me, I give it to you. You don't really trust it. You make sure that the headers above the pruning point validate correctly according to that data. So the proof of work you actually validate kind of enforces this information. So there's no real trust here, but nonetheless, it's called trusted data in the code. So, but another get pruning point so getting the pruning point anticon is another pretty expensive operation, because how do you get the anticon of a block? Can you like try and think about it for a second? Like, how do you get all the parallel blocks of a specific block?
I mean, you have it in the
is important because we kind of, so not exactly. So each block has the holds the can easily access the anticon of a specific, like for instance, the selected parent. So you can look at the other parents and realize and traverse your past until you're accessing the past of your selected parent, and that set is the anticon of your selected parent, but it's the anticon of your selected parent from your point of view. Following blocks might see additional blocks on the anticon of that block. So finding the anticon in general is kind of requires looking from the tips of the DAG, right?
Yeah.
Sense you can have, you need there's no shortcut, no easy shortcut. So this algorithm actually like traverses the entire it does it efficiently. It doesn't access full headers. It does it through relational info, but it actually goes from the virtual, from the tips until the pruning point and finds all the pruning point anticons. The reason we need the pruning point anticon is we can only delete the pruning point past, but the pruning point anticon is actually data we need to save. So that's what we need to keep. Okay, so keep blocks. So this like we keep a few map hash block hash maps which indicate what keep blocks mean. All the blocks we want to keep full body for, including transactions. Then there's keep relations where we don't keep the block body, but do keep all the topological relations, the DAG structure. And then there's a set of blocks where we do delete the relations, but we only keep headers. And that's for the past pruning points. The sample of a block every 12 hours is kept forever. Because we actually also, besides superblocks, the header also has a field of pointing at the pruning point, so we can form a sequence of pruning points from now back. It's not exactly a chain because each block points like it's like a more actually free interleaved chains, whatever. But we keep, so that's like the flow. Okay. Is the font large enough?
Yeah, I see the code, but it's a bit hard to see the file names. But I mean, yeah. They don't get bigger, the tabs at the top. So I can see it's in the processor is pruning processor file or something. I don't know.
The code itself you can't see?
No, the code I can see. I can just not see the file names. Like the tabs are not getting bigger if I increase the size of the font.
Okay, I see. Yeah. Okay, we're mostly inside more pruning processor now, like pruning processor, processor.rs. Okay, this is not too critical. This is like, whatever, I'm going to skip this for now. It's not relevant to this task anyway, so this too. Okay, so how do we prune? So the idea is there's a special block named origin, which is always like it's like a virtual genesis, you would say, or it's the block. It's not a non-existing block; it's just a special hash, which is like the root of the DAG, local DAG. Any block we have would, if we don't have any of its parents locally because we pruned them all, would point at origin as a parent. So essentially, it's like the most bottom point in terms of topology we save. So the most efficient way, traversing DAGs is not easy, right? Efficiently, because in general, you can do a BFS. If you do a DFS, you're doing something wrong because the DAG is deep, linearly deep. Any DFS traversal of a DAG is doomed to overflow your memory one way or another. Especially if you do it with an actual recursive algorithm. Even if you use an explicit stack, it would be very costly. So in DAGs, in our case, we do BFS. But when you do a BFS, you have to actually hold like a set of visited blocks because you don't want to. You can get to some blocks in many ways, so you must maintain information of already being here. So you either keep a set of visited blocks, or the other. If that would be too big, you might need to keep a store and like keep a dirty. Keep like an entry of this a database store indicating you can actually I mean you can save the set in a database store if that's too large, but in general even if we like I described before, we do a traversal to find the anticon of the pruning point. So we do a BFS from the tips, and you save a set of all the visited blocks. But we're talking a few megabytes. Like even if we're talking a few million blocks, 32 bytes per block for the hash. So that's like 60 at worst, the worst case, 30 or 60 or 100 megabytes, which isn't significant for our purposes. Anyway, that's if you do a DAG BFS, but we have a structure which helps us optimize this and do this specific traversal more efficiently. So the reachability data storage has an actual tree structure. So each block saves its selected parent as a specific special only parent. And we also save the other side of the relation, the tree children, like all the blocks in my future, which actually selected me as the selected parent. So that's going to be my children set. Anyway, long story short, this tree is very efficient to traverse without keeping any set. We only need to go. It's a tree. It's a linear structure. We only need to visit it. We do it with a queue because this tree is deep. So we do a BFS, not a DFS up, but we do a bottom-up BFS using an explicit queue. And we actually go up from the origin, and a block which we need to delete, we decide how much information we delete based on the keep sets we have. And
so
once
you delete from past to future, essentially.
Yeah, older, yeah. Which is why this process can also be actually the process can crash, and you can just recover easily. The process would come back up, realize exactly the same set of keep, and it just would continue. It would go up again from origin to wherever it reached, and continue the pruning from where it was. So this makes it crash safe. And essentially, because you're going bottom up at the first point where you get to So retention period root is like the generalization of the pruning point. Like if you have a retention period set for 30 days, it wouldn't be the actual pruning point of now. It would be a pruning point from 30 days ago. But this is essentially the pruning point. And once we get to a block which is in its future, so is DAG ancestors, is retention period root a DAG ancestor of current, meaning is it in the past of it? That means we got to the future of the pruning point. So we don't need to queue any more children of this one. We can continue. So this eventually makes sure we exit the loop once we have no more queue. Blocks. Yeah, once we get to the fully into the future of the point. And below that point, we keep only according to the sets we have inside. So that's how we make sure we have the anticon of the pruning point explicitly saved. The future of this pruning point is going to exit here. So we know we're going to keep all the data we need. That's the process, more or less. Okay, so if we're not keeping blocks, if we keep blocks, nothing to do. If we aren't keeping blocks, so we delete, we acquire a bunch of stores, and we first delete the all the transaction data related stores. So the main one is the block itself, but also all the information related to UTXO diffs, acceptance data. So this would only be filled for some of the blocks. We just did it. So we prune data related to block body. That's the first. And then being in keep relations means we don't want to delete the relations. And we have, this is a map shows you the affiliated proof level. So it shows you the lowest. So keep relations in general is our blocks, either blocks we need for the DAA below the pruning point I described before. Those would have affiliated proof level 0. The affiliated proof level is the lowest level of which this block belongs to the proof. Okay, a block header can belong to the proof on several levels. So affiliated proof level will be the lowest such level. So the idea is if it only belongs to proof level 8 and above.
So this is related to the block levels that we talked about earlier in respect to the MLS.
Right. So each level has a separated level relations store. Maybe I should. So let's go back to storage. So you can see that relation stores are a vector. So we have a relation store for each level. So this is going to be like the vector is going to have 235 entries, more or less. I wanted to show you that too. So max block level. So max block level is 225, actually. Yeah, so 30 zeros. And on testnets, it's we only assume the higher number.
It's like 5.
Anyway, max block level would be that array I showed you. The storage one is going to have 225 entries in the case of mainnet.
So index 0 is essentially the block with 30 zeros.
Yeah. It's actually going to have 226. It's inclusive. It's the end.
Oh, okay. And the larger levels are not as full. Like, do you know what is the highest block ever mined? Like which level?
I actually published a post about this. Like I checked it out like a few. If I search my X, you would see, but then you would also see all my notifications. So I have a post on multi-levels and X, and I actually like plotted all the levels and they're on the full time frame. I think the highest one was either 70 something. I think 71 zeros maybe.
Okay.
Including the 30, like actually 71 zeros, I think. Maybe 72. Yeah.
Okay.
What happened,
So
it has an interesting structure because because hash rate grows exponentially, it grew almost exponentially. So like level 50 doesn't really have blocks from 2 years ago. It's all like from more recent.
Yeah, makes sense.
The dynamic is interesting. Yeah. I'll send it to you afterwards, or I can share it here, or someone else can find it. I think if you search my profile for superblocks or
on Twitter? Oh no, X it's called now, right?
on X. Yeah, on X.
Yeah.
Try and find it. If you think that's gonna help, should I show the picture?
Yeah, it's not super important. I was just curious. So like we don't need to look it up now.
Okay. So essentially I wanted to say that the DB relations store has both sides of the relations, also the parents and the children. And children are mostly critical for pruning because when I delete
the direction you walk. Yeah.
No, so the direction we walked in the pruning processor, we used the reachability tree children, which are different.
Okay.
There's only one instance of those. It's not like a per level. It's a global single instance of reachability data. And here I'm talking about the relations only, which is only like not keeping additional data, just keeping the parents. And then for each of my parents, I add myself as a child. So we have both ways we can go. And it's critical for deletion because when I delete a block, when I delete a block, I need to tell my children to delete me, to not treat me as a parent anymore, right?
Yeah, because you store them
you have to have the children. They have me as a parent. Okay, now I'm deleted. So if I don't have a reference to them as children, I don't know how to update them to delete me as a parent. It's like I need to know who my children are in order for me to be able to delete this block. I need to know who his children are because I need to update them and remove that block from their parent list. So I must in order to do that efficiently, I must keep the children of each block. So when I delete it, I know who to update. So that's kind of the main reason. I don't think we use children in actual processing.
But after you're done deleting the parent, you actually also remove the entry in that store.
Yeah. Exactly. Okay. Yeah. But that's exactly one of the challenges because the header can be easily optimized with a very simple scheme of like a range. Instead of having the full list for each level, you can have a level range. You can say, okay, this list of parents represents levels 0 to 20, right? Because it's always consecutive. So that's easy. But when if we keep the relation stores the same, it's not going to be a significant optimization because there's still going to be all of the inefficiency is going to remain on the relation stores. So it's only going to be a smaller. If we want to also actually update the relation stores in a more smart way and maintain information cross level sometimes, that's challenging. That's where I said I don't know exactly how to do that. I can think about it, but I'd love to leave that to others. That's a challenge of how to manage multi-level stores, which are currently unrelated to each other, but have a lot of shared information, especially at the first 20 levels. So, and that it's not, there's a lot of noise around that 20 is not definite. Like hash rate change that 20 to 19 or to 21. So you can't just say simple stuff. You need to know the actual information, and it's not so easy to just like say, okay, let's assume all 20 first level have all the first 20 levels have the same store, and let's just keep one of them, because it's not exactly the case.
Yeah, because you have all these connections between the levels, right? So you can also not just like repartition the database and just like throw away one file or something. You actually need to go into the stores and delete the entries one by one.
Yeah.
Or at least the way it's designed now.
Yeah. So what I'm saying here, let me explain this for a second. When you launch a new node and you sync, so you get the proofs, the full proof, and you get all the trusted information and the anticon, and you compose a DAG. So we have the reachability store. So we try and use all the information with all these headers and populate the reachability information as much accurately as possible. But for say we look at level 50 of the proof, we don't maintain the relation information for level 0 for those blocks. It's meaningless. We only have the sparse, like a few hundred blocks with 50 zeros. Okay, so we only care about their relations at level 50 and above. We don't care about their relations at level 0. Actually, most likely we're not going to have the parents on level 0. So when we get the proof and we compose the relation stores to begin with, we only for each block belonging to level proof X, we only add it to relation stores from X and above. So we're kind of simulating the same thing in pruning here. When we found that this block has an affiliated proof level, meaning it belongs to proof level 50 and above, so we actually go and delete the level relations below that point, because we don't need it. It makes no sense.
Okay.
So we preserve the semantics that for each level, relations represent a contiguous DAG area in that level. But we don't need the information below that. So this is when we don't delete relations, but we still delete relations from low levels. Even when we keep relations, so we're not going to delete reachability, we're not going to delete headers, we're not going to delete ghost DAG, etc. But we are going to delete level relations
that are below the level.
Below.
Yeah.
Like this would probably be if lower level. Wait. I think that's the equivalent and more efficient way of doing this without checking just a nitpick. But no, I want to illustrate the point. It's just saying that if lower level, no, it's okay. If affiliated proof level is 0, so the 4 is never entered. So then there's no deletion. Yeah, that's equivalent to what we had before. Anyway, okay, else is the case where we do delete relations. Okay. So here's the main point where I think I guess things can be optimized, and that's where I guess there's room for optimization in terms of the pruning process. So in the task I wrote not so long ago, so when I observed, like currently on mainnet, there's not so much block data. So I was interested to see. I was after mainnet switched to 10 bps, I was following to see pruning efficiency. So on my Linux servers and nodes I have on Linux are always very fast. Pruning is typically finishes like sub 2 hours, maybe even sub hour, depending how strong the server is. Like order of magnitude of 5,000 blocks per minute. Still not so fast, but it's not even close to the production rate of new blocks, so it's like very safe. And
Yeah, it will
when
eventually catch up.
Yeah. But when but on some slower consumer SSDs, like this laptop I'm working on, it was slightly slower, like 1,000 blocks per minute, where we produce 600 new blocks per minute. So still okay, but definitely something we should optimize ideally.
No.
So the thing you can clean up from here is that it's unrelated. It's not only related to block data. On testnet, I wasn't sure. Maybe the slowness is also related to a lot of block data, like 100 kilobytes per block is more significant in terms of information. Maybe it takes time to delete that for some reason. But from what I see from mainnet, it seems like it's about the header structure, the DAG structure, so that's where we can optimize.
No.
So the main idea is pretty simple, but what do you think?
What I think in respect to what? In respect to how you can speed this up?
Yeah, no, but I need to give you some more information before that. So I'm not going to torture you. So the current algorithms for deleting, like the most complicated one is the reachability, because we wanted to keep the So look, if you can you read the comment?
Which comment? This one?
Like the
You need to
documentation?
block permanently from the DAG reachability structure while keeping full reachability info for all other blocks. It is for any B, C, and then it's a bit hard to read.
Any other B, C, and G? DAG or chain queries are guaranteed to return the same result as before the deletion. Let's just go there.
Mm-hmm.
So it's kind of saying, okay, let's delete this block, but everything around it is going to have the same information exactly, which is untrivial. Like if data stored in this block helped you understand something about others, how do I explain it? 1 second. They'll have 44 in the audience, even though we're getting to boring parts. I'm joking.
It's also getting quite late. I mean, for me, it's already 11. So
Yeah.
I guess people
What's
maybe
your
also
deadline?
just drop out. I'm staying up long and having any issues with staying up a bit longer unless my daughter wakes up.
Yeah. Okay.
So I suspect that here you need to actually look at a lot of the relational data, how this block relates to other things before you can decide if you want to delete it or not, right?
Yeah, you kind of think of this block, even if you only look at the reachability tree I described. So you have to take this block and take all its children and attach them to its parent, in a sense. Like you have to make the shortcut. Essentially, when you delete a block, you kind of write in the order of the merge set or anticon around it degree of information. So if this block had if the DAG is on average 7 blocks wide, like it currently is, so each deletion of block for this algorithm would write to approximately 7 other to the storage of 7 other blocks. Not a big change, but it's going to write to 7 other entries. So what happens is that you actually delete all these blocks. We're looking at specific block, so and we're writing information to its neighborhood.
And then you're gonna delete the neighborhood as well.
Delete, yeah, exactly. So that's the inefficiency, the main inefficiency thinking of.
So it would most probably be better to build some batches or something where you do mutations in memory and then you write the batch later.
Yeah, exactly.
Instead of writing them one by one, because I mean you have like random read access, right, which is usually the slowest thing in database access.
Yeah. So theoretically, you would say, okay, let's design an algorithm. If you assume that you're only keeping very sparse information, let's design the deletion algorithm to delete in batches, which is one option. But like you say, there's no real need to do that because the memory mutation is insignificant. So it's actually not a big change in terms of code. Like our code is actually written in a sense that you have staging stores. Because when you make a reachability storage, when you do any reachability operation, like unlike the headers stores, it's not an append-only data. Like I told you, it mutates it mutates information in the proximity of that block when you add a block. And same goes when you delete a block. So we do it in a way that there's a database store, and then there's another store emulating exactly the same interface, which is a staging store, which actually keeps all the mutations in memory. And only when you commit the batch, you actually apply the changes at once to the DB. So current code does that per block. There's a batch DB, and we build the staging relations and staging reachability here, right? So this happened like we're already in the context of some block. We're building the staging relations and staging reachability, and then we make the change.
So this is always one block at a time.
Exactly. So we actually write all this information to a block and then delete a lot of it a second later. So if we can just playing around with this area and using the batch on a more
efficient way,
maintaining it through some number, maybe 100 blocks or something, might be a not too hard change, which might have significant value.
I think that should actually speed up things quite a bit.
Yeah. So I'd like to see more like actual number. You have to find the workstation where you're slow enough and benchmark it and benchmark the timing and actually like make sure that we're not. And supposedly it's supposed to work out of the box. Like the algorithms of the staging store should just work, but changing this might encounter some new edge cases never visited before. So in theory, there can be some kind of problem popping up when you do that. It's supposed to work. There's a lot of tests, very thorough tests around this area of deleting stuff. Like actually, like the test composes like random graphs and deletes and saves a complete like a closure, transitive closure information of all the relations in memory, and then deletes one by one and makes sure. So there's a lot of tests. Maybe the tests don't cover like the batch good enough. I'm not sure. Anyway, I'm just pointing it out. So if something doesn't work as you expect, have this star in mind that maybe have this pointer in your mind that maybe this area is also sensitive. But supposedly it's supposed to work, should work, and it's just about this one is about understanding how to manage the batch object
across multiple blocks. Essentially, you need to kind of
across multiple, and understand what to do, and maybe even I don't know. You might realize that if you do this naively, and you do have a lot of block data, and you're batching also a lot of deletions of block data, you might I don't know how significant it is for the delete that the value of the database has a big big byte area. I don't know. You tell me if you know anything about RocksDB in this sense. In this sense, how?
I think it actually has a significant impact because you don't just delete the index structure, right? But you also need to go into the database and null these values and essentially free them, make them available again. So the amount of data you're removing actually has a significant amount of influence, because we were also deleting when we were in IOTA and we had similar problems. That's why we switched to this kind of like partition database, but it's not so easy here with the MLS.
Yeah. So the write batch, as far as I know, because it's an atomic operation, the database must somehow have in memory the whole thing. One way or another, it must probably have the all of the information in memory. So if we like just throw a batch here of 1,000, it might work nicely on mainnet now, but when blocks are full, you're suddenly going to realize, oh, that's wrong. So anything done here needs to take that into consideration. You might want to separate the pruning of block data from and do it on different tasks, like delete block data locally per block, but batch the DAG part. So
the relations and all the other related stories.
Yeah. So it's a bit nuanced.
Have you guys looked at all the things that you can configure about RocksDB, like if it's doing sync writes and these kind of stuff, or is that just like the default RocksDB configuration? Because you can also tweak a lot of stuff under the hood.
Yeah, I know. Some other people have explored this much more than me. I completely agree that
because there might be some optimizations in there, because I think you can actually do this kind of batch deleting so it doesn't delete things synchronously, but kind of does that later. So it kind of just deletes the index structure, so you can't find the stuff, but it frees the data later, which makes the deletion.
You think it can actually batch the logic? No. Oh, you think maybe? Yeah, I don't know. That's part. Yeah, I was pointing out like what I described here is this one, like idea accumulate deletes in the staging reachability stores and commit a single large batch.
Yeah, but I think there's a way to maybe do that under the hood, kind of, that it does that for you. But then I think it could use some kind of write ahead log or something. So I'm not sure if that will actually speed things up.
Right.
Maybe.
So it's the same effect would be achieved also if you have a RAM layer. Like if you map you do a virtualization and you map disk to the RAM, which is really. And then the disk would the RAM would like swallow the frequent changes, and you only write eventually something more.
Yeah, and I think there's a setting for that, but I'm not 100% sure, because we've also been using like some other databases in replacement for RocksDB, and I think maybe it was that hit this feature.
So it's definitely part of the space to explore in order to
explore.
Yeah. But yeah, algorithmically, I think this is probably the point where we're a bit slow, because like we've had past experience with this, and for instance, in the past, we had all the children of a block saved under one key value entry in the database.
Mm-hmm. So and you always need to update the one.
Yeah, it had a quadratic cost. So eventually we switched all these arrays, which are mutated like and extended to to just using a prefix of RocksDB and maintaining an array in the database. So then the write became all of one.
Yeah,
that was like a significant optimization. So we've seen this quadratic to linear effect before. So it makes sense. Might be the case here. It's probably the most significant part here. So there's two. It's also about the reachability deletion itself, which is here, but also the relation stores here might be affected by this optimization.
Mm-hmm.
I want to point out the thing we call the naming is a bit confusing. There's staging level relations. There's staging relations.
My dog is tucked between the cables. Okay, and now it's freed. It made like weird sounds. So it's like, what's going on? Okay, I'm back.
Yeah, I took the chance to look at the comments. Okay, things seem okay. So not so more. I think we should finish like in around 20 minutes or so. That would be 2 hours. That's long enough at most.
Yeah.
Okay, I just wanted to point out the thing I call staging relations. It comes from a store named Reachability Relations store. So there's a different, so like I told you before, there's Reachability store, which is a global. It has it has reachability information. You can ask a reachability query to any header you have, including proof headers, like ancient headers. You can still query reachability of them to others.
But not below the pruning point.
No, also below the pruning point.
Oh, okay.
Also, the superblocks can also be accessed for reachability queries.
Okay.
If you think about it, we need them when we validate the multi-level parents of a header. We, in a sense, need to look at these headers, and we need to check things about them. The only exception is the pruning points, which we only keep headers for pure. Anyway, but relations are kept per level. But there is also another additional relation store, which we call reachability relations. It's kind of, you would think of it. Originally, it's exactly identical to level 0. Okay, it has the exact same parents and children like level 0, but the way it's pruned is more sophisticated. It's pruned and while preserving the parent-children relations in the prune DAG. Okay, so say in the normal multi-level relation store, if all your parents were stored on level 5, you actually don't point at their parents who may have not been pruned. You start pointing at origin. So we don't try and can reconnect like grandfathers to grandchildren and stuff like that. The relation store is like the originally starts from all the blocks, all your parents, and then once eventually they get pruned, they're deleted, and you only point at your actual parents that are still not pruned. But the reachability relations is maintained differently. So if I delete a block,
do you then update the hash that they point to origin?
Yeah.
Okay.
Like I'll show you just for if we look at delete level relations. So you'll see this here.
Yeah. Okay. You place the old value.
But when we delete reachability stores, we go into a different algorithm, which is more complicated. And here we actually reconnect grandparents to children. So in a sense, if I delete block P, so I make sure to connect. If for instance, I was the only parent at block C, and I have a parent block A, so deleting block P, I'm going to make sure that to connect C and A to have a parent-child relation from now on. And that is required in order for, again, it's only required for pruning. Like if you can see that because of the way reachability relations is stored, it keeps what we call the merge set, the updated merge set intact. And we need, in order to delete the block, we need the merge set. So it's a bit complicated, but if you go into the algorithm, you'll understand why the reachability relations are needed. Essentially, they're only needed for this deletion to be accurate.
Yeah,
so
that's what you talked about earlier, right? To be crash fault resistant. So if the whole thing crashes or whatever, you can continue pruning.
Yeah. But also in order, even if without speaking about a crash, just in order to delete the reachability information related to this block, I actually need to know what his merge set is, updated merge set is, because each block in his merge set holds him as a future covering item. I don't know if you saw that workshop. So essentially, in order to know where to delete me from, I need to go into my merge set. And so keeping the merge set is more complicated. Blah, blah, blah. Long story short, the reachability relations need to be maintained in a more tight way, which actually saves also edges which weren't in the original DAG, but more of saves any information needed to know the relational, the topological relation between blocks. And it's required in order to be able to delete blocks cleanly.
No.
So yeah, like we said, there's no need to reinvent this algorithm and actually redesign it to have batch deletion, which is more efficiently, because we assume that the most of the cost is disk write and not in memory. So by just batching the DB operation and having the staging store, essentially the staging store is going to squeeze this information one way or another into a smallish number of mutations to be applied. When you commit. The way it's written is that you have the staging relations, and you apply the delete to this store, and then you do something. And then you do this commit. This is where we actually flush all the operations into the walksDB batch object.
Mm-hmm.
This is where we flush. This is where we apply the full write. That's more or less this story.
Okay. That's actually quite complex. You need to do a lot of steps in between just to get rid of the old data.
Yeah.
So, do you have anything else that we should cover? Did we cover all the things we had in the roadmap?
I wanted to look at so deleting subDAG segments while keeping superblocks. Wait. On various levels without losing their topological relational info. That's why it's not something touch. So we want to delete single block and update the neighborhood. That's what we do now. Instead, we want to process and write batches of errors at once. Should yield a quadratic to linear decrease in write. Algorithm can be kept logically because most of the cost is probably this kind. I don't think block data is the issue, but that should be verified. Might be another optimization point. And like we said, you might need to fine tune the way you do batches if you try them, not to include too much data for many blocks at the same time. Header compression schemes show header. So the compression scheme is pretty simple, I would say. It's not a consensus change. It's saying, okay, let's save something like instead of having so you would have, I guess, a vec of I just think about it the most naive way. So you would save like a range of levels for which this spec hash represents the parents. And then essentially you would map the header we saw before. So you would actually start from 0 and iterate until you see a level which is different, and then store 0 to that level with this array, and then go on. So it's like a pretty simple mapping, I think. And it obviously has all the information. So wherever this is used, you might have, like there are places where you access parent by level and you get an index of the level. So if you want to avoid
I think in memory, you maybe want to have the old way of representing things, right? Because otherwise you need to touch quite a bit, but maybe it's possible to actually compress that before, like that you kind of expand this photo representation to the concrete one.
If you keep it in memory, it becomes easier because you only need to do the mapping when you serialize and deserialize. But on the other hand, if you have this, I mean, you can do a binary search to find the level, or you can have a compromise where you save an arc of you can do all kinds of stuff.
Yeah, you could also, for example, do like diffs, where you say you inherit stuff from your parents if it doesn't change, and you just express what changes actually. But I think you still want to commit to the full data eventually. Like what is being signed should be the full representation. It's just what you want to exchange over the networks, maybe compressed.
So hashing, for instance, we're not talking about a consensus change. Like if the hasher is doing this iteration, so we're going to map, even if you save the parents by level differently, you're just going to iterate.
Yeah, okay, you're going to iterate differently. Yeah.
Iterate in the same way and hash everything in the same way. We don't want to change hashing. We don't want to make a consensus change. So it's not like a consensus change. So yeah, I agree there's different degrees of where you can put the line at, in a sense.
Yeah, but also for things like Nepo powers, potentially, it's good to have the full expression like it is now. So
it's easily accessible in the same way. I mean, you can do a binary search over these because they're going to be in order. So you can do a fast binary search per level and get to the same information.
Yeah, that's true.
So I don't know. I'm not like definite on this, but there's a few like areas. There's, like I said before, bandwidth can be first benchmarked and measured. We have a few. We have a few. I don't know. Yeah, it's something to explore. We have utils. Under utils, we have tower. So there's a middleware to inject inside gRPC.
Mm-hmm.
And actually, like that, we use it currently to track like amount of bandwidth used. I don't know if this is needed, but maybe you need to enter such a point in order to see the size of the actual data as gRPC compresses it compared to the full header size. So this can maybe help. That's where I would start looking if I want to understand, or maybe someone else has another suggestion. Maybe an Axim or Coder can say something about this. Like, where would you inject code to measure the size of the actual data and compare to the original header? So that would help understanding if we even need to touch RPC for this optimization. But disk, when we write a disk, we don't use any compression. So the disk obviously would benefit from this.
Yeah.
Now, there's a few points. First, like if you want, in general, just saying, like if you look at the headers store, so if you don't want to break the DB, you don't want to do an upgrade, you can support somehow. Either you do a DB, like if you do such a change to the serialized header, you need to manage the way you deserialize old and new data. So just like a point to notice, it's like a slight challenge for this task if you change the way you serialize. So this is the most simple approach, is to say, okay, let's require a full sync, a new DB scheme. But so either you do a DB upgrade. We don't want to do that. We want running nodes to be able to upgrade without resyncing. So either you have a DB upgrade procedure running on startup, where you save all the headers, you iterate all headers and save them in the new format, and then just have this store normally. The other option is to somehow manage two stores. It's all encapsulated under the DB header store. So you can have internally like new headers access and sometimes fall back to checking the old store, etc. So there's all kinds of ways to manage the upgrade of the header structure. Not so easy, that's why I'm pointing it out.
No.
But in general, it's easier to update the header. It's pretty straightforward, like I said. It's going to be like a consecutive range of levels where you're going to have the same back. And once you see the difference, you start a new entry and so on. And it's easy to go back to the original representation from that data. So you just iterate the range and duplicate. So that's that. The more challenging part is like I told you, the looking at the relation, per level stores and optimizing that. That's more challenging because of the way each level store is managed in a different way. They may like it might be the case where one block you delete the block for header 9 for level 19 and don't delete it for level 20. So what happens then if you saved them originally in the same database entry and there's only one of them mutated, you might need to clone and becomes more complicated, obviously, because now the stores each level are managed separately, and you would need to manage them in a different way. So that's a heavier change. But I'd say maybe this task can have like a few stages where you first start with database header stores, which is more straightforward. Maybe even starting without changing the header itself, like you said, so it make it easier. So only optimize the right.
I think it would make most sense to actually break it down into several PRs, right? So you can also look at these changes in isolation.
You still have the challenge of DB upgrade, but no. We have a DB version, of course, so you can always do like a DB upgrade procedure, which is probably the easiest path. It would mean that node operators who restart with the new version have some phase at the beginning where it's not going to be so fast. It's going to actually be writing all headers all over. So that's the cost. The alternative is to manage two stores under the header stores, and fall back and try the first one when you access the header and fall back to the previous one if it doesn't exist. That might be the easiest, actually.
Yeah, but I think the cleanest would actually be an update procedure, right? Then you don't have any old code garbage in the new version.
So, yeah, but eventually, like a few versions back, when you make sure, a few versions back, you stop supporting that, and someone who upgrades from who hasn't upgraded for such a long time, it would need to resync or do something more dramatic to his database. It's not like you don't keep it forever. You keep it for a few versions, and then But I agree, it has a cost of like double query when the header does not exist, because you need to check both stores.
No.
The other option is maybe I don't know, if we can use like the same, maybe we can serialize the new one, and when we deserialize, like fall back, like it would error somewhere. I don't know. It's probably too dangerous to rely on deserialization errors to fall back to the old scheme. I don't know. Something to break your head on, I guess. Yeah, but that's it.
I think we've covered quite some ground. Thank you for all the details.
Long enough.
And thank you for all the people that listened.
Fresher wants to know what staging stores are. So if you look at the reachability under stores,
you have the staging, the memory, and the database version usually, right?
Yeah. I think the memory is only used for tests. So it's simple in-memory store. Fully. Then you have the database, and then you have the staging, and they all implement the same interface. And then the query. All the reachability algorithms operate on an abstraction of the store. So there's a complete separation between the algorithmic logic. So the interface of the store was designed so that the algorithm logic can rely on the interface very accurately, and it can operate very precisely. But the stores themselves can have varying can be much more complicated. If in the staging case, it's a more complicated structure. But there's a separation between the algorithm layer, which is mostly inside processes, inquirier, reachability inquirier, and the reachability store where you can have the staging. So the staging store would essentially accumulate all the mutations, and when you commit, it's going to write to the DB relations, to the DB store, and the caches it manages. The caches are managed within the DB stores. The staging is another layer of cache of the mutations. You commit the staging to the DB store, it also updates the caches and the underlying stores. And so if it's a batch operation, it only updates the batch, and the DB itself gets updated when the batch is flushed.
It's essentially a temporary way of collecting mutations and committing them all together atomically.
So it's actually composed of a few objects. For instance, there's a staging set entry. Like the reachability information is composed of. You can have the children of your reachability children of this block, and you can have the future covering item set of this block, and each one of them can be a staging set entry with additions and deletions. So this there's a staging set entry representing the mutations of the specific set, where a set can be either a future covering item set or a children set. And then the staging store itself can have staging children. It's going to have a hash map from the block changed and the staging set entry mutated for the children, for the future covering set, etc. So the staging store is holding like a lot of information and various degrees of block hash maps, etc.
But that's not deduplicated, right? So if I would, for example, have an entry that updates a value and then I have another entry that actually deletes it after, this is not going to be like compacted to then not do the update and just do the delete.
Yeah, so I'm not sure. No, it is going to delete. If you add and then delete, as far as I remember, it's going to delete it from the added mutations.
Oh, okay.
Maybe it's not. I think I did it right. And even if that's not the case, it was done. So there's very carefully, and when you commit, is the order of how you apply the mutations is critical. So you go, for instance, you do deletions always after mutations. So if there was a mutation and then a deletion, obviously the delete is going to apply, is going to be the winner in this sense. So the order in which we commit is critical. But as far as I remember, there are various places where I don't know. I think whatever is not compressed is just done in order. So yeah, it might grow a little more than the optimal, but it should be okay. That's where the code is. I'm not going to go over it now, but that's what you should look like. So it has the main points are where it implements the write interface. So here it's implementing the trait, which is staging reachability store. That's the writer one. There's there's a reachability store. So there's reachability store reader and there's reachability store. So reachability store is the one with the write functions as well. So the complicated code is in all the write functions, how they operate for the staging, how they update the staging data. And then the next thing to look at is the commit. That's the next thing interesting to look at. And this object encapsulates the complexities of the specific set. So it had enough complications to justify another struct. So maybe not enough documentation here, but that's more or less that's the staging reachability. And there's also a staging relations store, which is much more simple, but and the other places, there was the place where I touched on this, these relations. There's also under processes relations. There's where there's few deletion algorithms, which are also like reachability. They're kind of separated from the storage layer. So the stores can be implemented in various ways, but the delete level relations is the operation making sure that the delete is consistent, that we also deleted the child of the parent, and we consistently updated the area. So that's an algorithm which is implemented abstractly above any store implementing relations. So there's also a separation here between the process, the algorithm, and the storage. So that's what. Anything else, Fresher? Okay, no more requests. I think it's long enough. And we should probably fold. It was really nice.
Yeah, I really enjoyed it. It was very informative. Thank you so much.
Let me say goodbye for a second. Wait.
You can see it's also slowly getting dark here. Before it was still bright. But the sun is going to go up in like half an hour again. So
when next workshop? When you go on. No. But I'll take that, or we should take that as a compliment, I guess. I'm not.
Yeah, I mean, we should do this more often, I guess. There's still a lot of code. I mean, even if I've already looked at some parts of the code, I guess it's also very informative for people who are maybe not that familiar to get like a deep dive into these kind of things.
Do it more casually also.
Yeah.
Just get on and say, okay, you're asking me about something or anyone else, and you want to, and I realize that it's going to be more efficient if I walk you through the code, so we can just go on stage.
Yeah. So
then
let's do this more often.
Yeah, sure. So it was great seeing you, everyone, and thank you for joining.
Yeah,
and
same.
This is
Thanks for having me.
Rusty-Kaspa performance